Let me begin by saying that calculators are not merely as smart as you think they are. They're just clever. For example, instead of memorizing the shape of each and every possible function and output, like sine and cosine and tangent and 2 to the x, they make use of pretty darn good approximations. They can take sine of x and turn it into this. They can take e to the x and turn it into this. They can take any number of functions and turn them into a sum of much more easily computable numbers. This, my friends, is the concept of a Taylor series, an incredibly powerful tool in math and calculus that allows you to turn any function into an infinite sum of polynomials. And while it may sound scary, the idea behind this isn't that difficult. It's all about mimicking the rates of change of a function as much as possible. As such, you'll need a bit of calculus knowledge, namely the power rule of derivatives and the derivatives of sine of x and cos of x, which you can pause and see here. For reference, the derivative of f of x, which we denote as f prime of x, is the slope of f of x for every value x. It's a powerful tool that you can apply multiple times to a function to get info about its rate of change, and the rate of change of that rate of change, and so on and so forth. This idea of successive derivatives will be crucial to our understanding of Taylor series. Let's try to define them for ourselves. Let's try to approximate sine of x. To do this, we need a starting point, a piece of reference. Let's say 0, 0, to make things easier for ourselves. And I'm going to try to make a function made up of the sum of a few simple polynomials that can mimic that point as much as possible. Let's line up 4 powers of x, each with their own coefficient. A plus bx plus cx squared plus dx cubed. Now, of course, when x is 0, I want y to be 0, so we already know what a is. Now what? Well, as I said, we want to mimic the rates of change of this function as much as possible. In calculus terms, I want to mimic the derivatives of this function. So I take the first derivative. B is now the only one without an x. In some sense, it is now its turn. Meanwhile, we have the derivative, the function that represents the slope of sine of x at all points. The slope of sine of x at 0 is therefore cos of 0, or 1. So I want this sum of polynomials to be equal to 1 when x is 0. Evidently, this necessitates b being 1. Do the same for the second derivative. You can see that the second derivative is 0, so c must be 0. Do it for the third derivative, which must be negative 1, and you notice a pattern of counteracting the successive applications of the power rule. 3 times 2 times 1. And the more you do this, the more you will see that eventually you must divide out by 3 factorial, then 5 factorial, since the fourth derivative is 0 again, and you will continue to have to do this back and forth of positive and negative signage, only for the odd terms, so on and so forth. From a graphical point of view, each term we add on produces a better and wider approximation for sine of x. We can do a similar process for any function. We can do it in real life. If we know the first 3 derivatives of how a potato is cooling at a certain point, we can approximate its temperature around that given point pretty well. And the starting point doesn't have to be 0 all the time. We can approximate anywhere if we know the derivatives at that point. The way we change our formula is now we, of course, use the derivatives at that point, but we also shift our x value in order to center ourselves on that point, and make sure that when we plug in that center value for any derivative, that we only have one term in the spotlight. Amazing, huh? Taylor series extend in usage beyond BC calculus and theoretical maths. They're used in physics and computer science and calculators and iPhones. And hey, if someone asks you to show them sine of x, but you only remember the derivatives at one point, you know what to do. Thank you.